All right, hello and welcome. Today we're going to journey about 100 kilometers straight up, right to the very edge of space. Why? Because we're on the hunt for a mysterious, powerful rhythm in our planet's atmosphere, a hidden pulse that beats with this really strange but fascinating regularity.
So here's the central puzzle we're tackling. Way up there, there's this enormous, planet-wide wave of energy, and it surges in strength exactly twice a year, almost like clockwork. Now, for decades, scientists knew this was happening, but they couldn't for the life of them figure out why. What in the world could be causing this bizarre, semi-annual beat?
Okay, so to solve this mystery, we first need to get a handle on the phenomenon itself. What exactly is this massive wave that's pulsing through our sky?
What's called the atmospheric tide. You see, every single day, the sun warms our atmosphere, and that causes the air to expand. This expansion creates a massive, globe-spanning wave that travels all the way around the planet. You can almost think of it as the Earth taking one giant, slow, daily breath. But here's where it gets really weird. Even though the tide is a daily thing, its strength changes in a big way throughout the year. Observations showed that way up in the Mesosphere, that's a layer about 50 to 85 kilometers up, the tide's power would spike around the equinoxes in March and September. And then it would get a lot weaker. Nobody could quite explain this twice-a-year pattern.
So how do you even begin to investigate a puzzle that's happening so high up you can't see it or easily measure it? Well, you build a virtual atmosphere and you start running some experiments.
The key to cracking this case was a really sophisticated computer simulation called a linear tidal model. Now, this thing basically let scientists become atmospheric detectives. They could create a virtual version of the atmosphere, and then, and this is the cool part, they could turn different forces, like solar heating or global winds, on and off just to see what impact each one had on the tide.
The investigation, naturally, started with the most obvious suspect, the one force that creates the tide in the first place, the sun.
So the model was designed to test two main factors, or two prime suspects, if you will. First, you've got the raw power of the sun's heat. And second, you have the powerful background winds that are always flowing through the mesosphere and the lower thermosphere.
Now, logically, solar heating makes a ton of sense. Around the equinoxes in March and September, the sun is shining directly over the equator. This focuses all its heating power right where it can generate the strongest possible tidal wave. And yeah, the model confirmed this. Heating alone does create a twice-a-year pulse. But it was too weak, and the timing didn't perfectly line up with what we see in the real world. So the sun was definitely part of the story, but it wasn't the whole story.
Okay, so if the sun isn't the whole answer, what about our second suspect? For a long time, scientists thought the background winds were just too slow to be a major factor. Turns out they were looking at the wrong thing entirely.
And this quote from the research paper, this is really the breakthrough moment. The model revealed that the tide was incredibly sensitive to the mean winds, a factor that had been, kind of overlooked before. This was the big new clue.
You see, the crucial factor wasn't the speed of the wind itself, but something called shear. Latitudinal wind shear is just the difference in wind speed at different latitudes. So imagine you're on a highway, and the lane right next to you is suddenly moving 50 miles per hour faster or slower. That sharp difference, that shear, that's what creates a really powerful effect way up in the atmosphere.
And this, right here, is where the mystery finally gets solved. It was never just the sun, and it was never just the winds. The answer is in the incredible way these two forces interact with each other to create the atmosphere's hidden pulse.
It works like this. First, the solar heating creates that basic twice-a-year pulse. But then, this pulse has to travel up through those high-altitude winds, which act like a kind of gate. During the solstices in June and December, you get really strong wind shear, and this acts like a bottleneck, squeezing the wave and weakening its energy. But during the equinoxes, that wind shear dies down, the gate opens wide, and it allows a much stronger, more powerful tidal wave to shoot right on up. So the winds don't create the pulse, they just amplify or suppress it.
And this table right here, this is the final proof, the smoking gun. When the simulation ran with only the sun's heating, you get a partial match. With only the winds, you also get a partial match, but the timing is all wrong. But when the model included both the solar heating creating the pulse and the wind shear acting as the gate, boom, the simulation produced a strong semi-annual tide that perfectly matched what we see in the real world. Case closed.
So, we've solved this really fascinating atmospheric puzzle. But
what does learning about a wave 100 kilometers up really mean for us, down here on the surface?
Well, this discovery is absolutely crucial because it shows just how interconnected our atmosphere really is. Energy that's generated by sunlight, way down near the surface, can be totally changed by winds 100 kilometers higher up. This whole process is a key part of how energy gets moved around our planet. It also showed that our global wind data wasn't quite perfect. It was missing the strong shears needed to explain this effect, which really highlights the need for even better, more precise measurements to improve all our climate and weather models.
At the end of the day, it's a powerful reminder that our planet's systems are woven together in these incredibly complex ways that we are still just beginning to understand. It really makes you wonder, right? What other hidden rhythms and secret connections are playing out right now just above our heads?